Let's practice what we learned in this module. And for that, consider the following example data. Let's say we have a patient because we're setting up a database for the application we work with in our hospital. So we work with patients in there, and this is how a patient record could look like. We got first name, a last name, an age. We got history, which is an array of embedded documents. So here you see that combination I was talking about. And you can fill the blanks here with anything you want, like treatment, write any text you want, or use a number because you imagine having some number code for the different treatments you have. It's really just about practicing how to interact with that data. And this is what I want you to work with. The tasks for you are that you should insert 3 such patient records into a new database with a new collection with at least 1 history entry per patient. A history entry simply is that array in here. So simply make sure you have at least 1 nested document, disease, cold, treatment, whatever you want, in that history array. 3 patients with at least 1 history entry per patient in a new collection, in a new database. Once that is added, you can find it with the find command, see if that looks good. And I then want you to update patient data of 1 patient only by identifying it in some way that works for you, with a new age, name, and 1 additional history entry. So simply add a second entry if you want, or overwrite his history. This might be easier than adding, because that's something we haven't learned yet. Simply overwrite history, name, and age. The history can be overwritten with a history with 1 entry or multiple entries, whatever works for you. After you practiced updating, I want you to find all patients who are older than 30 or whatever works for you. If you gave all your patients an age of 18, maybe, update some to have different ages and then pick a fitting filter. So basically make sure you train finding your data with a filter that does not fetch all patients. Thereafter, make sure you delete all patients who got a cold as a disease. And for that, might be worth adding different diseases, or, you are fine with deleting all your patients. So basically, you'll practice all the CRUD operations, embedded documents, and lists in here. Good luck! Make sure to compare your solution to mine with the solution video you find in this assignment. So let's start with this assignment. And first of all, we need a new database. So I will use a new database and I'll name it hospital. You can name it however you want, of course. Now in there, I want to insert 3 patient records. And for that, I will create my patients collection by accessing it on the database. And then I'll add insert, and you can either insert 1 multiple times or use insert many here, whatever you prefer. I'll use insert many, and in there, I'll insert my patient records. Now you can structure this however you want. I'll define my first name, Max, my last name, Schwarzmuller, my age, 29, and then my history. And that history is another array, so an array of data in here. And there, each history entry should be another nested object, a nested document. This nested document will then have a disease key, maybe cold, which is a string, and then treatment. And here I'll use a number, because I imagine that in our hospital, we have number codes for the different treatments. Now this is 1 history entry for this 1 patient. The patient ends here after this curly brace, and I can add another one with a first name of Manu, last name of Lawrence. This is my colleague in this course, age of 30, and another history. Now, I won't bore you with typing this, so I will skip ahead. Simply add your own dummy patients here with your own history. I added all my entries here into insert many. And now if I hit enter, you see this looks good. And now we can simply access patients with find and pretty to see what was inserted. There I see all my patients with their names, age, and their disease history. And for me, every patient has just 1 disease with a treatment each. Of course, you might have multiple entries. This was task 1, 3 patients with at least 1 history entry. Now let's update the data of 1 patient, up to you which one you use, with a new name, age, and history entry. Now, you can choose whichever patient you want, and you can also choose how you want to select the patient. ID would be the cleanest way of doing it because you're guaranteed to have a unique ID. But if you get different names, as I do, you can of course also select by name. So let's say Maria is what I choose here. And then I want to access my patients collection, update. And here I will use update 1 because I know I will only update one patient. And I'll look for the patient with the first name equal to Maria. The second argument here, after the comma, defines how to change the patient with $set as you learned. And in there, I'll change the name. And let's say I'll go with the last name because I had a typo. That is Blake's instead of Blake. So I added an S. I'll change the age, let's say to 27. And I'll change the history. And I'll overwrite it with a new list. And if you just wanted to add an element to the list, this is something we'll learn later. So for now, let's overwrite it with a new list, with a new nested document in there, with a disease of very sad, which of course is sad, and a treatment of 61. If I now hit enter here, this was accepted, one document was modified, and if we print all patients again, we see Maria has the S after Blake, is now 27 and very sad. I don't know if that's an improvement, but at least it's task number 2 solved. Task number 3 is that we find all patients who are older than 30. Now, I got no patient who would be older than 30. Manu is equal to 30. So what I will do is I'll go with older than 29 here. Choose whichever filter fits your data. So here I'll have my patients, and I'll find all patients by passing a filter here who are older than 29. My filter is that I am looking for the age, and since I want to have greater than and not equal, I pass a document as a value, and I use a special operator, $GT for greater than, and the value I use here is 29. Now let's pretty print this, and we indeed only find Manuel, who's 30. This is task number 3 solved. The last task was to delete all patients who got a cold as a disease. And in my case, that's only me, Max. So this one. Now to delete all patients with a cold, I could of course look into the database and say, okay, I'm the only one, so I will use my ID and I will delete myself by that ID. Well, that does not make much sense. The idea is that we don't have to fetch the data first. So instead, I'll go to my patients collection and say delete. Delete many, because maybe I have multiple patients with a disease of cold. And now I simply pass a filter where I need to drill into that nested or embedded document. And this can be done by looking into our history and there, and this is now really cool, into disease. So even though history is an array, you can simply select a nested property, a nested field like disease with the dot notation. And MongoDB will automatically check this on every element in that array. Just important, wrap this with quotation marks. And here I'm looking for equality to cold. So now all patients who have at least one history entry where the disease is cold will be deleted. If they had multiple history entries, so if I would have another history entry with another disease, I would still be deleted because I have at least one matching entry. And keep in mind, delete many does not delete the embedded document just because we're checking the embedded document. It always refers to the overall document. This is just our filter criteria. So if I hit enter, you see one element was deleted, and if I output all patients here, we indeed only see 2, Manuel and Maria. And this is the assignment solved, and I hope this made it clear how you work with the data, with MongoDB, with nested documents, and all that fun stuff. That's it for this module. We had a detailed look at databases, collections, and documents, and what all these things are. That a database holds multiple collections, and each collection can then hold multiple documents. This is how MongoDB structures its data. Databases and collections are created lazily. That means only when a document is inserted, only when you need a specific database or collection. A document can't directly be inserted into a database, it's always part of a collection, so keep that layered architecture in mind. Documents have a certain structure. Each document needs a unique ID, which has to be called _ID. You can set this on your own or take the one MongoDB creates for you. And you can have embedded documents as well as arrays, as well as texts, numbers, all the other data types you already saw and will dive in later in this course. An important part or aspect of working with a database is that you can perform CRUD operations. That stands for create, read, update, and delete. MongoDB offers multiple CRUD operations for a single document and bulk actions. You can insert one element or one document or many documents. And you can find many documents or find one document. Some methods require arguments. Insert one, for example, needs to know what you want to insert. Other methods like find can use arguments, as you will see and as you already saw in this module, but don't need one. Find, by the way, also returns a cursor, not a list of documents. That cursor is useful for manually going through the documents because otherwise all the documents, which could be thousands or millions, would have to be transferred over the wire in one go, which would not be that great for your bandwidth and your connection. You can use filters on find and also on update and delete to narrow down which documents you want to find or you want to update or you want to delete. Last but not least, talking about retrieving data, you should be aware that you can use filters and operators. Filters and operators basically allow you to narrow down the set of data you found, like the greater than operator, and you can identify all these special operators provided by MongoDB by the fact that they start with a $sign. And this allows you to simply limit the amount of data you're fetching. And you can use projection to then take the data you fetched and tell MongoDB which fields you actually want to get and which you don't want to get. So filters allow you to restrict the amount of documents. Projections then allow you to restrict the amount of fields per document, so to say. These are the basics. Let's now move on. Now with the core basics set, now that you know how you can basically insert data, read data, and so on, and that you also saw how you can explore your data, let's take a step back and start at the basis or the start of any project. And there you'll have to decide how you model your data. How do you plan to store your data in the database? Which relations exist between your data? And how should these relations be reflected in your database? These are all important questions, and these questions will impact how you use MongoDB and how you structure your data there. Therefore, in this module, we'll have a look at document schemas and understand what's up with these and how you can create document schemas or define document schemas. And we'll also have a look at the important data types MongoDB offers to you, because data types like text, numbers, but also some advanced types like dates and so on, are of course crucial to enable you to store exactly the data your application or your use case needs. We'll not stop at these data types in the general document schema though. We'll also have a look at relations between documents or your data. Because in most applications, you got different entities. Things like, let's say, when you're building a blog, you have posts, you have users, you have comments, and all these entities are related. And these relations need to be reflected in your database too. And you will see how that works in MongoDB in this module too. And last but not least, having an idea of how your data should look like is nice, but you also want to validate incoming data. So all your inserts and updates, you want to validate whether the data getting written there fulfills your requirements. So for example, if that age of a user really is a number. And you will learn how you can perform schema validation in this module too, therefore. Let's start with document schemas. And there's one important question. Wasn't MongoDB all about being schema-less and enforcing no schemas? It is. MongoDB does not enforce any schemas. Your documents can look the way you want, and you can have totally different documents in one and the same collection. Let me show you an example for that. Here I'm again connected to my local and now cleaned up MongoDB server. I simply deleted the data we wrote in the last lectures. So I got a clean database here, a clean server. And I will simply switch to a new database, which, as you learned, will be created on the fly, on demand. So I will switch to a new database and I will simply name it shop. Because imagine we're building the backend for our online shop and we're now modeling the database for it. Now in that database, I'll probably have a products collection where I store my product data. And there I will insert one product, a new document therefore, with, let's say, a name, and I'll simply name it a book, and a price. And the price might be double, so a number with decimal places. If I now hit enter, this gets acknowledged, this gets inserted, and it gets this automatically created unique _ID field, which every document requires. And now we obviously have it in there. Now let's add another product. And what we can do in MongoDB is that this product looks totally different. So there I might have a title, which is t-shirt, and I might have a seller, which is a nested document, let's say, an embedded document, with a name of Max and an age of 29. Now, this is a totally different document. It still could describe a product, though the price is missing, but maybe it's free, we don't know. And if I now look into my products here, by simply finding all products and pretty printing them, we see we got these two products in one and the same collection. And this is fine. MongoDB will not complain about that. You can absolutely do that. You can mix totally different schemas, and the schema simply means the structure of one document. So how does it look like? Which fields does it have? Which types of values do these fields have? That is what is a schema. So we got totally different structures or schemas, as you could call it, in one and the same collection. And that is fine. As I mentioned, MongoDB enforces no schemas. You can mix them. But in reality, you will probably have some kind of schema. Because if you are building the backend for your online shop, it's in your interest that all your products have a price, for example, that they all have a name which is stored in a field named name. Because if you then write some application code, let's say in PHP or in Node.js, and you retrieve your data from your database, you obviously want to cycle through that data and output it into a view which you render to the user. And to cycle through your data and access your data, you need to know in which field which data is stored. So you will most likely have some kind of schema because you as a developer want it, because your application needs it. So whilst you're not forced to have a schema, you will probably end up with some kind of structure. And that is the important thing to understand. You got total freedom, total flexibility, and if you need it, use it. But in reality, you probably will have to think about how your data looks like, because your data will need some kind of structure so that you can work with it efficiently. Let's have a look at that schema thing, and let's think about the options we have. So obviously, we can have a totally chaotic approach, as I showed you in that last little example, with totally different documents in one and the same collection. Or we follow a SQL world-like approach, where we make sure that all elements, all entries have exactly the same schema, and there is no extra entry on any document. So we got the whole bandwidth, and we also got some shades in between. So in the chaos world, we basically got what we just saw in the little example. We got maybe a products collection with totally different products in there. So that is possible in MongoDB, but it's probably not what you need or what you'll use in reality. Maybe you're somewhere in between. You got some kind of schema. For example, here all my products have a title and a price, but you got some extra information on some of your documents. So there is maybe some extra data on some documents, but the general schema is the same. And there probably are some core fields which exist on every document. Well, or you got the other extreme, where all documents have exactly the same structure, like here. Now, anything is possible here. You can go with any of the three solutions or any step in between, depending on how you need it in your application. But in reality, I guess either the approach on the right or most often the one in the middle is what you will see in reality. Because there you use the best of both worlds. You have some structure because your use case, your application probably needs it, but you also take advantage of the flexibility MongoDB gives you so that you can store extra information. That, by the way, is also possible in the SQL world. There maybe you would have a null value for some fields. Well, in the middle world, you simply omit a field if you have no data, and you assign a value to the field if you do. So that is really a mixture. In the end, go with whatever works for you. The case in the middle and the case on the right are the more realistic ones, or the ones you see more often in reality, I guess, though. Back in my collection, let me quickly clear my products here with delete many. And there I'll simply pass an empty pair of curly braces to delete all my entries so that now it's empty. And now in there, let me again insert some products, insert one. And I want to show the two approaches which are the most realistic ones. Let's go with the middle approach first, which might be the one you see most often. There you have a name, like a book. You got a price like $12.99, and that's maybe it for the first product. And then you enter another product, and that product also will have a name and a price, because these are probably some core fields which every product needs in your application. Because on the page you render to your users, on a website, let's say, you probably want to show at least a name and a price. So for our other product, t-shirt, simply the value changes, but the fields are the same, and the names of these fields also are. Whoops, I hit enter accidentally. Of course, I should enter a price here, like $20.99. So now if I look into my products here and I pretty print that, we see both elements are in there. Now, this is the case on the right, the SQL world. We got exactly the same structure, just the values differ. Now, you might have another product, let's say a computer, and of course that also has another price, like this. But this might now also have an extra field, details maybe. Let's say in your shop not every element has details, because maybe a book for some reason doesn't require details. Obviously, you could argue a book and a t-shirt also have detailed data, but this is just an example. Let's say our computer has some details, because there we basically have the CPU, and that is a text where we have Intel i7, some build number. Like this. If I add this, and now I find all my documents, we are in the middle world. We got a core structure which every document fulfills, like a name and a price exists on every document. A little side note here is that the price actually does not always have the same kind of data. It looks like it always has a number, and that is true, but we switch between a double number, so a number with decimal places, and an integer, a number without decimal places, but that's a side note. I'll come back to data types. So generally we have the same though, name and price, but then we got some extra information on one product. And that might be something that works for your application too, because there you could of course have some code which always displays the name and the price, but only displays the details if available. And therefore we can reflect this in our data, and we now are in that middle column of the last slide. So this is one of the more realistic cases you'll have in MongoDB, and this is a totally fine way of using it. Well, all the use cases were fine, but this is one you'll encounter in practice too. Or of course, you have exactly the same fields for all your products. Just to showcase this real quick, I'll again go into my products database and delete all my products in there with delete many. And let's say we want to have that same structure we had before, but now we want to have that in a way where all documents have exactly the same fields. And that is possible. If I repeat my insert commands here for the book, we would simply set details equal to null. Null is a value which you can assign to indicate that, well, there is no value. but there is the field available then. So if we do that, and we do the same for the t-shirt here, so we also have the details set to null there, and I then also enter my computer. If I now find all products and pretty print them, we see the difference to before is that we still have no details data for the first two products, only for the third one. But now we still have that field in there. That is the more SQL-ish approach, I'd say, because the structure is now exactly equal in all documents, except for that number thing which I mentioned. The price is a different type of number, but otherwise it's exactly the same structure. And this might also be an approach you use because you like the clarity of having exactly the same fields everywhere, and you simply indicate that no value is available by setting the value to null. Now here you can take either approach. It's probably a bit more MongoDB-ish to simply get rid of details if it holds no value, but ultimately this is also up to you, and you could take this route too. There is no single best practice here. You can go with whichever approach works better for you or whichever approach you personally prefer. So now that it's clear that we are free to define a schema for our documents and to structure them in exactly the way we want them to be structured for our use case or application, let's have a look at the different data types we can use in MongoDB. So basically, the types of data we can save in our fields in our documents. There we, for example, have text. We already saw text data types in this course. Text always uses these quotation marks around the value. And important here, I'm talking about the values, so the part on the right side of the colon in your JSON documents. So you can save text like names. You also got no hard limitation here. The only limitation you have regarding the maximum amount of characters in your text are the 16 megabytes overall size for the whole document. If your text is greater than that, well, then your document becomes too big and your text is too long. We also have booleans. Booleans are simple values, true or false. Is something the case or not? Is a user an administrator or not? You could save that as a true or false value, and that value is called a boolean. Another core data type are numbers, of course. And actually, we got a couple of different numbers in MongoDB. We got integers, for example, and you see int 32 here because MongoDB knows different kinds of integers. Int 32 integers are integers that are 32 bits long, and therefore if you try to store values that are longer than that, they will overflow that range and you will end up with a different number. For longer numbers, MongoDB has a solution though, a long number, an int64 integer, which you can also assign to store values. In the shell, by the way, if you just enter a normal value, it is treated as a float value. That is because the normal shell, as we use it in the course, is based on JavaScript, and JavaScript doesn't differentiate between integers and floating point values, so values with a decimal place. Therefore, everything will be stored as a 64-bit float value in the shell. That is the default value, and we'll play around with that a bit and see more of that in the numbers module of this course. But be aware that MongoDB is able to store smaller integers and bigger integers. The solution you choose here, of course, kind of defines how much space will be allocated and therefore how much space will be eaten up. And you also can store decimal numbers, so numbers with decimal places. I already said that the default in the shell is to store a floating point value. You also got a special type, number decimal, and that is provided by MongoDB to store high precision floating point values. Because normal floating point values, also called doubles, are basically rounded, so they're not super precise after their decimal place. For a lot of use cases, it's enough though, like for prices in a shop, you got enough precision for that. But if you're doing scientific calculations or anything like that, you might need a very high precision, and there is a special type that offers this very high decimal place precision, where you got 34 decimal places, so after the comma, which are not rounded but guaranteed to be correct and precise. It's simply a computing limitation that we got no 100% precision all the time, but that rounding occurs. Now, besides these basic values, even though some number of values here already are a bit more advanced, we also got the object ID value. The object ID object is a special object automatically generated by MongoDB to give you a unique ID, which is not just a unique random string, but also a string that contains a temporal component, so that if you create two elements after each other, two documents after each other, you are guaranteed to have the right order due to that ID, because the older element will have an ID that comes prior to the other one. So there is this sorting built into the object ID because it respects a timestamp. Speaking of timestamps, you can also save a date in your database. There is a special ISO date type which you can use. You can construct a date and save that to your database. And that is then a date which you can work with to do date calculations and so on. And there also is a timestamp type. The timestamp is mostly used internally. You can create it automatically. Mostly you let MongoDB create that for you. And that is guaranteed to be unique too. So even if you create two documents at the same time, they will not have exactly the same timestamp, because it will basically take into account the current time and then also add an ordinal value so that two documents at the same time still don't get the same timestamp, but respect the order in which the insert command was issued, for example. So you got that timestamp too. And you could say that object ID kind of is based on that timestamp and then just uses some algorithm to spit out a seemingly random string. Last but not least, you saw that you can embed other documents. That's of course important too. You can embed documents, and these documents can then in turn embed other documents or hold any fields with any of the values you see here. And you can also have arrays as values. And the arrays are simply lists of values. You can have a list of strings, a list of booleans, a list of numbers, or a list of other embedded documents, or even a list of lists, a list of arrays. That is possible too. So these are the data types. And throughout the course, you will see them again. So we'll work with them. And for example, there will be a whole module where I will work with numbers to give you a feeling for why we have these different types of numbers. In the next lectures, I just want to play around with these types a bit and give you a feeling for how we create the more advanced types like dates here and how we can save them and work with them. Okay, so let's now play around with these data types a bit. I'm on my MongoDB server again, and I dropped all existing databases. You can, by the way, always do that by switching to the database, like test if I had that database here, and then executing drop database, db.drop database. And this will get rid of the database if you have it. But let me now clear the screen, and let's now use a new database, companies, or company data maybe. And in there, let's say I have a companies collection. And in that companies collection, I now want to insert one new company. And my idea here is that for this company, I want to showcase some of these data types. So that company will probably have a name, and that name will be some text. Now, as you learned, the text is enclosed in quotation marks, and you can, by the way, use double or single quotation marks here. This does not matter. That is the case in the shell here, because the shell is based on JavaScript. For the programming language you're using with the MongoDB driver, that might differ, of course. So here, let's give this any name, like Fresh Apples Inc. It's a company I just came up with. And now with that company name added here, what else could we add? Well, let's say this company is a startup, and therefore we add a is startup key here. And this simply is, well, true. So here I'm using a boolean because the case or the question whether this is a startup or not can be answered with yes or no. And translated to a boolean, that would be true or false. Here it's yes, so it's true. Now, besides that being a startup, let's also log its number of employees. And I'll add 33 here. So this is a number, and this is actually an integer, you would think at least. Now, the shell which I'm using here is based on JavaScript, and JavaScript doesn't differentiate between integers and floating point numbers. This would be a floating point number, by the way. So this will actually be stored as a double or float in MongoDB. Not as this number decimal special high precision thing I mentioned on the slide, but a normal floating point number with some imprecision on the decimal places. Now that might be fine. And for now, let's simply store it like that. Let's also add a funding here, and let's store a very large number there. And I'll actually store a number which is easy to remember by just sliding over my numbers twice. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and then again. Let's also add an embedded document here. Details maybe. And there we could simply have any additional data we want, like CEO, Mark, Super, obviously a good name for the CEO. And let's also add a list. Tags maybe. That is an array. You always add an array by using square brackets. And there, in turn, we can add any value we want. So this can hold multiple string values like super, perfect, whatever you want. It could also hold numbers, and all the values in the array are just separated by commas. Or it could, of course, also hold other nested documents. So this could hold other documents with tags which are, well, basically documents with a title that then holds the value. So whatever your application needs is possible. You're really flexible here. So here I go for the embedded document in an array style. Now, besides these values, we also learned about dates and timestamps. So if we also add the founding date here, we can construct a new date in the shell by calling new date. And if we add it like this, it will take the current date. And I will indeed do that here. We can also add a timestamp, like inserted at, to give that a clear timestamp when this data was inserted, by calling new timestamp. Now, these are functions, new date and new timestamp, that are provided by the shell. There are equivalents in the drivers for the different programming languages though, and you'll find the exact methods you need to call in the driver docs. Here, for example, I'm on the page of the MongoDB Node.js driver, and there I can click on the reference of the latest release, and of course such release references are available for all drivers. And in the documentation for the driver, you find detailed instructions on installation and how to use it, and you should also find an API documentation, which is simply a list of all the features that are included. And in there, for example, you also find long and int32, that will be useful methods or objects when working with these values. And you also will find something that helps you with a timestamp, for example. So down there, if you click on timestamp, you open the timestamp doc and you'll learn how you can create a timestamp in that Node.js driver. So there by calling new timestamp after importing the timestamp from this MongoDB driver. And more information on that and how to use that driver and so on can, as I mentioned before, be found in the general driver docs, like the tutorials here, the quick start, or the general reference here. So that is how you can use these types you'll learn about here in the shell in your driver too. So the shell here is based on JavaScript, therefore here we actually do use new timestamp to create a timestamp. And with that, for now, I added all the data I want to add. If I now hit enter, this gets inserted. And now let's have a look at it by finding one company, so the one we just added. And here we see that company was added. We see the data we added. We see, for example, for the date, we got this ISO date object with the current date I'm recording this at as a value entered here. You see it uses the year, month, day format, then a T to separate the time from the date, and then we got the time in a 24-hour format stored here. The set at the end marks the time zone for which this time is logged. You also see that timestamp object, and as I mentioned, this is actually a timestamp based on the current time in milliseconds, and also it has an ordinal component, so that if I were to insert two elements simultaneously with insert many, they would have different timestamps. Now, one super interesting thing can be seen if we have a look at funding. There you see that the number that is stored is actually not the number that I added. If I scroll up a bit, you see that for funding I did add 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, twice essentially. So I rolled over the keyboard twice. But the number that was stored is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6, 7. And then it's essentially nullified or cut off, you could say. The reason for that is that I tried to store a number that was too big, because the normal number JavaScript accepts is essentially a 64-bit floating point value, and that could not be stored here. And that is a restriction you can face when working with numbers. If you need to store super big numbers, you'll have to store them separately, maybe as a string. Now, speaking of numbers, you saw some general values here on the company. Now let me get a little bit more abstract so that I can show you what's up with these numbers. And I have a whole module where I also talk about numbers and how to work with number data. But for now, let me quickly add some dummy data. I'll use a new collection for this, numbers, and this will be one of the rare cases where I'll just use an abstract example. I'll insert one document here, A1. Now, if I insert it like this, obviously if I access numbers and I find one element, we see it here. Now, one interesting thing can be seen if I now use db stats. Stats is a utility method provided by the shell which outputs some, stats about this database. Here we see how many collections we got in there, how many objects, and we also see the average object size. Now, I got 2 collections in there, so let me quickly get rid of the company's collection by calling drop on the collection. Like drop database gets rid of a database, drop on a collection gets rid of that database. If I now repeat stats, we see there's only one collection there, and we get a data size, an average data size of 33. Now remember that value of 33 here. Now I will use my numbers collection and delete all elements, so the one element I got in there. If I now execute db stats, we obviously see data size 0 because there's nothing in there. Now let me repeat that insert one command here, but I'll not insert a number like this, which remember is stored as a 64-bit floating point number by default, but I'll use a special method provided by the shell, and you find equivalents in your driver docs when working with a driver, which will create an int32 value instead of that default 64-bit floating point number. And if I store the same number, 1, now with this helper function, and I repeat my stats output, you see that it shrank a bit. And this is one of the reasons why you could consider using these special values provided by MongoDB, because you're able to manage your data size a bit more efficiently. Now, it's also worth pointing out that this was only stored as this 64-bit floating point number because the shell is based on JavaScript, and JavaScript doesn't differentiate between integers and floats. Other languages do. So for other languages, this might not be the case if you accessed your database through their driver and added a number there. For the shell, it is, however. And this is good because here I can show you the difference between the default number, the float, and this integer. You can also check the type of a value as it is stored in MongoDB by using the type of command which is provided in the shell. There I can access numbers, find 1 to get that one element I have, and then access the A key with .a. And we see the type here is number. Now, I don't want to go too in-depth into that whole number thing, also because it has a lot to do with computing in general and not so much with MongoDB, but I found this important to highlight that you have these different formats. Often it might not matter, and the default which is stored might work for you. Like for all the numbers we used thus far for ages or prices, we can just enter the number and it will get stored in the database. The sizing difference might not really matter for us. The extra precision we could get on the decimal places will also not matter for only 2 or 3 decimal places. So there we will be fine with the defaults. I want you to be aware of the general set of data types you have, and that there are specialized data types for specialized kind of operations you might plan. You should also not miss the BSON types document, to which you find a link in the last lecture of this module, where you can learn more about the general data types MongoDB knows and how it can store data in its database, and where you can then also learn more about some of the special data types like object ID or timestamps, and which in general is a great backup if you want to dive deeper into a specific data type or learn more about a specific data type. Now that we understand that we can use schemas and that we probably will use them because our application typically works with certain types of data, certain schemas, and that we had a look at the data types you can use, the different integers, text, and so on. Now that we had a look at all of that, let's see how we can think about modeling our schemas. And I want to give you some guidelines or hints that you can keep in mind when you think about how should I structure my data. We'll not look at relations yet. I'll come to that next though. But thus far, let's see what we got. One important question is, which data does my app need or generate? And the term app definitely should be understood in a very broad sense here. This can be a mobile app, this can be a website, it could be a smart device generating data, like a tracker, a fitness tracker sending GPS coordinates. So this is a very broad definition of app. The idea is my business model, you could say. Which data does it need and or generate? And that can be anything: user information, product information, orders, coordinates, anything like that. And this will define the fields you'll generally need. And of course, also already a bit how they relate. A user might order products. So this gives you the general frame for your data structure. You then also have to think about, where do I need my data? So for example, if you're building a website, do I need it on the welcome page, on the products list page, on the orders page? And which kind of data do I need on all these pages? Because the idea with MongoDB is that you store your data in the format you need it in your application. And if you need the same data in different formats, you want to find a good structure that covers all these use cases, or if absolutely necessary, you could even split it into multiple collections. So this defines your required collections. For example, that you have an orders collection for the orders page, that you have a products collection for the products page, and it also defines which fields you have in the documents of a collection and how you might group these fields together, so how you might relate these fields. More about relations in a second. You also should ask yourself, which kind of data or information do I want to display? So on these different pages, which kind of data do I want to show on there? And that again defines which queries you will need then. So do I display a list of products or a single product? Is it a find or find one query? How should I configure this query? Am I looking for a product with a specific ID, or am I looking for all products? And Manual will take a detailed look at how you can configure your find queries to narrow down the set of found products, of course. These queries also, or the kind of queries you plan, also have an impact on your collections and your document structure. Because as I already said, MongoDB really embraces that idea of planning your data structure based on the way you'll retrieve your data, so that you don't have to do complex joins, but that you can retrieve your data in the format, or almost in the format, you need it in your application. You also need to ask yourself, how often do I fetch my data? On every page reload, or every second, or not that often? Because that also tells you if you should optimize for easy fetching, because you're fetching a lot, but maybe you're not writing data that much. So you might be fine with having some duplicate data if that speeds up the fetching process, because you don't have to join data manually. Or do you often write and change your data? If you have an application where your data gets changed a lot, or parts of your data get changed a lot, you want to ensure that these parts of the data that do get changed a lot, let's say we have a lot of orders, but the product metadata doesn't change that often, you want to make sure that your orders are not unnecessarily duplicated across collections, but that you have one collection with your orders where you can write new orders too. Product metadata, on the other hand, might be distributed across different collections because, well, you don't change it that often. So if you change it, you have to touch multiple collections, but that's no problem. The main focus is that you can fetch that data from the different parts of your application in the format you need it. So these are some things for you to keep in mind or to think about. And if that is a lot right now, that is totally normal. No worries, we'll see all that throughout the course, and we'll have many examples so that you can get a feeling for, well, how you might approach that and how we would structure data in a certain scenario. And one important thing that is related to these questions is, of course, the question about how you model relations between different entities in your data. And that is what I'll take a look at next. So we had a look at the general data structure, but always only for one collection and the documents in that one collection. Typically, you have multiple collections though. You might have users and products and orders. So if you have multiple collections that still are related, of course, or where the documents in these relations are related, you obviously have to think about how do you store related data. Do you use embedded documents? Because that, of course, is one way of reflecting a relation. If a user has an address and that address consists of a street and a city, then you might have a nested address document in the user document. Or do you work with references? Here are two examples. As I just said, we might have a nested document, an embedded document. Here are my customers. And by the way, of course, in JSON, the field names like username, age, and so on would be enclosed in double quotation marks. I'm just leaving that out here to save some space. So this is not a real JSON code, but it is the structure of the data. And here, my customer has an address, and that address could totally be stored in a new collection. But we can also embed it into our user or into our customer here because it's strongly related to that customer, and we might want to fetch both at the same time, or at least have an easy way of fetching both if we need to. The alternative is that you use references. Let's say we still have customers, and each customer has a list of his favorite books, and we could absolutely go with nested or embedded data. So here we have an array with embedded documents, and each document is shortened here, but each document could be a book with a title, a price, an offer, and so on. Now, the problem here is that we will have a lot of duplicate data because different customers can have the same favorite books. And if we then change something about that favorite book, we'll have to change it on all customers. So instead here we might go for references. We might have a customers collection and a books collection. And in the customer, we still have that array of favorite books, but there we only store the IDs of the favorite books. That means that when we fetch the customers and we also want to fetch the favorite books for the customer, we have to run two queries. That is correct. But on the other hand, if we change a book, we don't have to change it on 10 different customers, but only in the books collection. And the ID will never change, so we never have to change or touch the favorite books array in the customers document. So we have that relation through a reference. Now, you got these two different approaches. And now the obvious question is, when should you use which? Time to have a look at some examples. Here's example number 1. We had a kind of related example earlier in this course already. Let's say we're creating our database, our application for a hospital. And there we got patients and their disease summary. So every patient has one disease summary, which belongs to that patient only. And there is only one summary per patient. So we're not talking about the history we had earlier in this course. It's just a summary. Something like is ill, had previous diseases, and a list of previous diseases, things like that. So one summary per patient, and of course this is a one-to-one relation because the summary of patient A can never belong to patient B, and the other way around. How could we model that? Back in a brand new cleaned up database server, I'll switch to my hospital database, which will be created on the fly, and there I want to create my patients collection, or to be precise, I want to insert a patient. So let's insert one patient. Now let's say a patient simply has a name, Max, a age, and then we have that disease summary. Now let's go for the reference approach first. Disease summary could be summary max 1, any identifier you want. So here I'll go for that ID approach. We can insert that, And obviously, if I now inspect my patients with find one pretty, we see that one patient in there without pretty though. That is not existing there. So we see that one patient in there. Now let's also create another collection, disease summaries. And then there I'll also insert one summary. There I'll explicitly define the ID and use my own ID, summary max1. I could have also gone with the automatically generated object ID, but then I should have generated the summaries collection and that entry first so that I could take that object ID and use it as an ID on the patient. I did it the other way around, so I'm using my own ID here. And there I'll simply add my diseases array, which simply lists all diseases I ever had. And let's say that's a cold and that's a broken leg, which I never had, but anyways. So now I added this too, and now of course I can access my disease summaries collection here, find the one element that is in there, and this is the element I just inserted with my own ID. And that ID of course matches the ID I stored as a reference on my patient. Now let's say in our application, the website we're building, the mobile app, whatever it is, we now have a request where we need that patient and also the disease history, or the disease summary, I should say. So we might have an incoming request, which in the end, by the MongoDB driver, is translated to a find request. So we first of all find our patients. And in reality, we'll probably do that by looking for, let's say, all patients with a name of Max. Or here, as a shortcut, since I only have one, I'll just use find one. The thing is, in the end, we have some query that returns Max here. So that is my returned patient data. The problem is I'm also interested in the disease summary. So I also want to get that. Now what I can of course do is, in my application, I can access disease summary and therefore get my key here. And in the application we're writing, in PHP, .NET, Java, Node.js, whatever it is, we can of course fetch some data from a server and then store that data in a variable. So let's say here in the shell, we can do this with the var keyword. We have our DS ID for disease summary ID, and that simply is the result of patients find one, and then they're accessing the disease summary. So now if we output DS ID, that is the ID stored in this patient. And now we can simply reach out to disease summaries, so that other collection, and there we want to find the first disease summary where underscore ID is equal to DS ID. So I can use that variable here. And I simply stored it in a variable so that I don't have to paste or add this long term here as a value for ID. If I do that, I indeed find my disease summary. The bad thing here is that this took 2 steps, and also from a performance perspective, this will actually be super fast. But if you have a very big database, a very big collection of patients, and a big collection of disease summaries, this might not be the optimal way of doing that. Splitting that across 2 collections feels a bit unnecessary here. The better approach in such a case, where we have a strong one-to-one relation, would be to use an embedded document. So let me actually reach out to my patients and delete all patients in there. And now let's insert that patient again. So that insert one command from earlier where I inserted Max. Now I will not insert a disease summary, which is a reference, but instead I'll insert a nested and embedded document here. And now that embedded document would have my diseases key, my diseases field, with the cold and the broken leg, like this. And now the huge advantage, of course, is that in the application we're writing with whichever language we use, I can simply write my query to find my patient by ID, by name, or in this case, as a shortcut, simply with find one, and I will get all the data I need, the patient data and the disease summary data. So this is an example for when you would use an embedded document. You have a strong one-to-one relationship. Now, in the last lecture, we saw a one-to-one relationship where we want to have a embedded document. Now, for many, probably most one-to-one relationships, you'll probably go with the embedded document. But you're not forced to. You could also have one-to-one relationships where you still opt to use different collections. And here is a possible example. Let's say we got a couple of persons and a couple of cars. And I'm not talking about car models here, so not BMW, Mercedes, Ford. But let's say we have a person and the car this person owns. And therefore, this is a one-to-one relation because this car cannot be owned by a different person. And that person could, of course, theoretically own multiple cars. But let's say each person can only own one car. So we have a one-to-one relation then. One car per person and one person per car. Now, we could, of course, still model this with an embedded document. In a brand new MongoDB server, let's add a new collection. We use car data, whatever you want to call it. So that's the database. And now let's add a new collection there. And we could go for persons and insert one person here. And that one person will have a name, Max, let's say, and we'll have a car. And that car is a nested or embedded document where I then have the model, BMW, and let's say a price, 40,000. Now, of course, I can fetch my persons and get back the car with it. And that might be fine for a lot of applications. But let's say we're not creating some web app where we need to render both on the same screen, but maybe we have more of an analytics use case. So we have a use case where we are very interested in analyzing person data, like average salary or age, all data I don't have in my dummy data here, but we can, of course, add more data depending on the app. So we're interested in analyzing our persons, and we might be interested in analyzing our cars, but not so much in the relation. That might occasionally be interesting too, but maybe we also want to do a lot of averaging, a lot of analytics on the persons or the cars. So here we have an application-driven reason for splitting this up. There is no hard reason. It's perfectly fine theoretically to merge that into one collection as we are currently doing it, but due to our application needs, this might not be optimal. Because if we're only interested in the cars, there's no need to fetch all the persons just to get to their cars. That would actually mean we have to do a lot of transformation work to extract the car data, and we send a lot of unnecessary data over the wire. And the other way around too. If we're only interested in the person data, I don't care about the cars. So we again would have to do a lot of unnecessary transformation work. So such an application-driven requirement or need could be a reason for splitting this up. For other applications, merging it might be perfectly fine. So here, we could go for an approach where I delete all persons just to clean it up. And then I again insert a person again, insert one. But this time, let's say that is our person with the name and the age and the salary. Like this. And now we have a possibility of fetching all the persons. Typically, we would, of course, have more than one and do any analytics on that. And if we're interested in the cars, we have these in a separate collection. So there we can insert our car data, like model, BMW, price 40,000, and then here also maybe the owner. And that could be a reference to some ID we define. Or here probably we would go for the ID which we have, the automatically generated object ID. So let's store that. So now we still have the possibility to relate the car to an owner. That is possible. And in the person, we could now also store the ID of the car if we wanted to, depending on whether we often will have fetched persons and now also want to get the car, or the other way around. We got some link. That is the key takeaway. So we can merge the data if we want to, but if we commonly don't do that, we don't have to use an embedded document. We can go for different collections here. So that would be one possible use case where you use different collections, even though you could perfectly embed it. We had a look at one-to-one relations. Let's now have a look at one-to-many relations. Let's say, like in the Q&A section of Udemy, we have question threads, And each question thread then has a couple of answers. So an answer only belongs to one thread, but a thread can have multiple answers. That's a typical one-to-many relationship. How would you model that in MongoDB? For that, I'll create a support database, and in there, I might have my question threads collection, and there I insert one new question thread in the end. There we might have like a creator, Max, so the person who opened this thread. Then we got the question. How does that all work? By the way, not how you should pose a question. Bit more details, please, but that is the question. And then we got the answers. And now the question is, how do we model the answers? We could go for a separate collection with the answers and only store the IDs to the answers here. So there we could have Q1, A1 as an ID, and maybe we also have Q1 for question 1, of course, A2 as an ID. So now if I access my question threads and I find that one question I have in there, we see we're now taking that reference approach again. We have an array of IDs. And that would mean we would now also create an answers collection and there insert many answers, because now I want to have 2 at least, because I have 2 references here. So to complete the demo, let's insert 2 answers. I assign my own ID because I'm using my own ID. Again, we could have created it in a different order and then used the object ID in the answers array here. But here I'm doing it like this. And then we get an answer with the text. It works like that. And I will insert a second document. Important for insert many, we wrap the documents we insert in square brackets. So we insert an array. So the second document in that array then also has an ID. That ID is Q1A2 to fit that reference we stored. And there the text is thanks. And obviously an answer would probably also have like an ID of the person who created it or the embedded person data. But let's not worry about that right now. If I hit enter, the 2 elements were added. And now again, we can, of course, look into our answers and see the 2 answers there. And we can then manually match that as we did it earlier. We could retrieve the question threads, and on the question threads, we could now simply store the different IDs and the answers in variables and then make requests to the answers collection and look for these IDs. And we don't have to make 2 requests. Later, Manuel will show you how you could also search for all elements that fit an array of IDs you're looking for. So you don't always have to look for one ID. You can say, hey, give me all documents that are this ID, or this ID. So it's still one extra request though. Here, again, embedding might be the better solution. So in question threads, I'll first of all delete all existing documents to start from scratch. And now again, I will add my question thread with insert 1 here. Now again, probably I'll have a creator. I have the question text. How does that work? And then I have my answers. And the answers now are not references, but a list of documents. And there I could have my first answer with the text like that. And then I have a second answer, so a second document in the list of documents with a text of thanks. And now with that, if I save that and we open our question threads and look into the first question with find one, well, then we see now we have that embedded approach. Now a list of embedded documents, because it's a one-to-many relationship. So we have many documents, but still it's embedded documents which we're using here. And for a scenario like this, and a similar scenario, for example, would be posts and comments related to posts, makes sense to be modeled like this. Because often you need to fetch the questions along with the answers. So from an application requirement perspective, you want to fetch the merged data. And we also don't have thousands of answers on one thread typically. So we also don't have the danger of bloating our document and maybe reaching that 16 megabyte limit we have for a document. So that is not a problem here. And therefore, this might be a perfect use case for embedding documents in a one-to-many relationship. Now that we had a look at a one-to-many relationship where embedding made sense, let's have a look at a relationship, a one-to-many relationship, where splitting it in collections might make sense. Here, I got a couple of cities like New York, Berlin, and so on, and I got the citizens. Let's say we have a database, a collection, which holds all the major cities of the world, and then a list of every person living in that city, like the registry of the state where all people are registered, let's say. So we got something like this. The problem we'll face here, theoretically, that would make sense to be a one-to-many relationship where you embed your documents. But from an application perspective, you might often be interested in fetching all the cities with their metadata, but you don't want to fetch all the citizens along with the cities. Because in New York, where we have like millions of people, that would be a lot of overhead data which we don't need, which takes very long to fetch, and which is a lot of data to transfer over the wire. And additionally, for big cities with millions of citizens, you might indeed hit this 16 megabyte limit for the overall document. And keep in mind, that limit counts towards the document and all nested documents. So it's not 16 megabyte per nested element, it's 16 megabyte for the overall document. So you might face this limit too, or might hit this limit too. So for technical and application reasons, here splitting it up might make sense. So here, you might have your city data database, and in there you have your cities collection where you insert a city, like the name, New York City, coordinates, which is a nested document with a latitude, and this is arbitrary, this is not the real latitude and longitude, something like this. And you store no data about the citizens in there. So you also have no citizens array in here with all the IDs of the citizens, because that would be a super long array too if you have millions of citizens. So you just have the metadata. And there I got a excess square bracket. So you just have that stored, and therefore if you find that one city, it looks like this. And you might also store the citizens, but you will do this, citizens, in a separate collection. And then there you might have your different citizens with the name, Max Schwarzmüller, and the city ID maybe, and that ID could be New York City to match it by the name, or you simply use that object ID, of course. You want to use something which is unique, so let's go for the object ID. So that would be one citizen, and then we have another citizen where you also have a name, Manuel Lawrence, and we're not really living in New York, but just as an example here, you store that like this. Now insert many needs square brackets around all the objects you're inserting, so don't forget to add these. Hit enter, and I got a typo. I was missing the closing parentheses after object ID. And now I inserted my citizens, and if I inspect my citizens, if I find them all, and I print this, here are my citizens, and now I can always retrieve just the citizens and match them to their city with the city ID if I need to, or fetch just the cities. And I'll not hit the document limitation of 16 megabytes for the city because I don't embed all my citizens, and I also don't unnecessarily fetch all the citizens along with the city if I'm only interested in the city metadata. Now that we had a look at one-to-one and one-to-many relationships, the obvious missing thing is one-to-many. So let's say we have customers who can buy products. So we're looking at orders. A customer might buy multiple products, and a product might be bought by different customers. So one customer, many products, one product, many customers. So this is a typical many-to-many relationship. How could we model that? To say it right away, often you'll model many-to-many relationships with references. So let me again create a new database or join a new database, my shop database, and there I might have products. So I'll insert a product here. That product will have a title, let's say, a book, and the price $12.99. I also will have customers. So I'll also insert a new customer into my customers collection. Name, Max, age 29. And now with that, we could create an orders collection. Orders to insert one order. And there we could now have a product ID and simply take that ID of the product we added. And we could have a customer ID and take that customer here. And now we have that too. Now this would be the SQL world approach, where we have 3 tables in SQL, and we have that join table in the middle, which matches products and customers. Now we can do a bit better, in quotation marks, in MongoDB. We can make it work with 2 tables only, so I can actually drop my orders collection. So DB orders can be dropped. So if you now find that, you find nothing because I dropped it and all the data in it. And with that dropped, I still have my products, by the way. So we still have the products and we still have the customers. So with these 2 tables, I can now add orders without adding a 3rd table. And for that, I'll go to my customers, let's say, because typically I want to add that relation on the customer, because you could say, yes, the product got bought, but actually customer is the active person. And it's more realistic that you're fetching the orders for a given customer than that you want to display orders for a given product. But that would be possible too, and you can use that approach on both tables here. So I'll show it on the customer, and I'll simply update my customer here. Obviously, you could also insert a new customer with existing orders. So I'll update the customer with $set, and then add orders here as an array. And now every order could simply be an object where I have my product ID, and that still is the ID I have up there. So I use this ID down there, and then maybe something like the quantity. We could have also added that quantity to that 3rd in-between table earlier, by the way. So now if I do that and I find one customer, you see now we have the orders, and that might look like an embedded document because it is, but actually we're still using a reference approach here because we did not embed the product data. We just added some metadata for the order, but I'm just referencing the product data. So we're using a reference-driven approach here, and we could add the same orders array to the products if we want to match it the other way around too. So both is possible, or either of the one like we have it here. So now we have a many-to-many relationship with references with 2 tables, which would be the MongoDB way of displaying or creating such a many-to-many relationship with references. You could also argue that you don't necessarily need to use references here. Often you will, and if that's your use case, it's fine. But let's have a look at the embedded alternative. And for that, I'll update my orders array here, and that will replace it. It will not add this element. We'll see how we can add elements to arrays later. For now, we'll replace that orders array with a new one, with a new array of documents of orders. Here, I now have a title of my product, because say I fetched that in my application when the order was placed, with the price $12.99. So I'm manually copying this, so to say, and a quantity 2. Now if I look into my customers collection, we do have an embedded document. This is now not a reference-driven approach, but I embedded the product data along with the metadata for the order. Now, what could be a disadvantage of this approach? A disadvantage is the data duplication. We got the title and price of that product in orders here. And keep in mind that this user might order this product multiple times and other users could do. So you will probably duplicate this data a lot. And if you ever change that data, you not only need to change it in the products collection where you store it, and that is the product data which is displayed in your shop for users to buy it, but you would also have to change it in all the orders. Well, or do you? And that is the reason why such an embedded approach might be fine here. Once the order was placed, even if the price changed for the product, we will not change it for the existing orders, right? The people don't have to pay more after they bought it. So the price here is locked in anyways. The title might change a bit, but do we really care about this in our orders? We might not care. It's not going to change from a book to a t-shirt because it's still the same product in the end. It still has its own unique ID, and we would probably also store the ID along with the product here, by the way. So probably we don't care about a title change too, because if it's a nice book now instead of a book, it doesn't really matter for us. So if we have an application where we kind of take a snapshot of the data anyways, we might not worry too much about duplicating that data because we might not need to change it in all the places where we did duplicate it if the original data changes. And that, of course, highly depends on your application. For a shop and the products and the orders, this might make sense. In other use cases, you might absolutely need the latest data everywhere, and we'll have a look at such a use case next. But I want you to not automatically say many to many, I will use a reference. Instead, think about how do you fetch your data? How often do you change it? And if you change it, do you need to change it everywhere? Or might duplicates be fine? So in the last lecture, we had a look at a many-to-many relationship where changing data might not be that bad for our duplicates, and therefore embedding the documents might be fine. Now let's have a look at a many-to-many relationship where splitting it up and using references might be better. Here we got a couple of books and a couple of authors. And one book can be written by multiple authors, and one author will probably write more than one book. So it's a typical many-to-many relationship. Now let's see how we could model that and how we could store that in our database. Let's create our book registry database here. And in there, I'll have my books collection. And I'll insert a new book with the name My Favorite Book and with some authors. And here, let's first of all go for the embedded approach. So I'll have an author, Max Schwartz, age 29, and I'll have another author. Name is Manuel Lor, age 30. If I hit enter, we can of course find all our books here, print them, and see we got embedded author documents. Now we'll also have our authors collection typically, because when we're managing books and authors, well, we'll need both kinds of data. And authors might then be a collection where we insert many authors with square brackets, as you learned, then multiple documents separated by commas. And there we might have name Max Schwartz. Maybe that also is our unique identifier we can use. Otherwise, we should also store an ID here in the authors of the book. But here we got that. We also got the age. And there, let's say we also have the address as an extra field with a street and so on. And we got the second author, which is Manuel Lor, age 30. And there we also got an address with a street like this. I can look into my authors, of course, with find and pretty print that, and I see my author data. Now that would be a typical use case. We got our books with embedded author data, and that could be all or some of the data we have in the authors collection, and we get just the authors collection. The problem is, if one author changes, maybe I got older, maybe I moved, then I need to update that everywhere where I used it. And that's not just the authors collection, but that would be all my books. And that is especially important, let's say, if I changed my name because I'm married. Then I can't say, yeah, I don't care, it's an old snapshot like we did for the orders. For the books and for the authors, I want to have the most recent data, of course. And if I'm displaying the age in the book, I might say that is a snapshot data, that is okay. For the name, it's probably not. And in my registry in the database, even the age is not okay. That should be all up to date for future books, for future prints, let's say. So here, if we then change the name of the author, we have to change it here with the update method in the authors collection. And we also have to change it in the books collection by finding all books where this author is an author. And that is a lot of work and a lot of write and update requests. This is bad from a performance perspective because we have to, write a lot to the database. It also is error prone because we might be overlooking some document we should update. And therefore, this is probably not the best approach for this scenario. Because in our application, if the data does change, it should change everywhere. Now, even with that, it might be okay if changes are very unlikely to happen. But some data, like the age, will change at least once a year. Other data might change more frequently. And the more frequent we can expect such changes, the more often we'll have to touch dozens or hundreds of documents, so the worse the matter gets. So low frequency might still let us get away with this approach and might make it a good approach. With higher frequency, it almost most certainly is not a good way of relating this. So instead of using embedded documents here, we should go for the reference approach. So we should take the references of our authors and then go to our books collection, update the book, in our case here, the one book we got, and update it by setting the authors to an array of our object IDs. So of the object ID of Max and the object ID of Manual. And now if we output our books here with find 1, now we only got the references in there, and this is better, because now if we do fetch all the books, we will have to merge it manually with the author data, but therefore the author data is guaranteed to be up to date, and if we change the author data, we don't have to do that in hundreds or thousands of documents. So these are your relation options. And I hope that the examples kind of gave you a feeling for how to think about relations and when to use which approach. It always depends on your application needs, how often you change the data, if snapshot data does suffice, and how large your data is, how much data you have. In general, with embedded documents, the idea is to group data together logically, and often that makes sense and gives you an easier time when fetching the data. And that is great for data that belongs together for one-to-many or one-to-one relations, and that is not really overlapping with other data, so you got no many-to-many relation, and where you're also not in danger to hit any limit imposed by MongoDB, and where you also don't need to split your data for application needs, like we had in the person and car example here. You should avoid super deep nesting because you can only nest for 100 levels, as you learned. And again, keep that 16 megabyte limit per document in mind. And that also contains the embedded documents. So it's not 16 megabytes per embedded document, but for the overall document. That is a lot, but for New York City with all its citizens, you would probably breach it. The alternative then is the reference approach. There you split your data across collections, and that is great for related data that is shared, so many-to-many relationships in the end, or it's great for data where you would have a lot of duplicates, which you'll update a lot, and therefore you have the danger of needing to update a lot of documents all the time, which is bad. And it's also a great solution if you need to overcome any nesting or size limits. Then you can simply split it across collections, because that, of course, basically allows you to remove some levels of nesting. These are your options. There is no general formula, but if you keep these general things in mind, how do I use my data? How often do I use it? How often do I change it? And how is it related? One-to-one, one-to-many, many-to-many. If you go through all these points, you should be able to really create relations that work for you. Now that we talked so much about relations, let me show you one useful operation MongoDB offers for merging related documents that you split up by using the reference approach, so where you got no embedded documents. And that is the lookup operator. Now, the lookup operator is used like this. This uses the aggregate method, which we haven't learned about. We got a whole module about the aggregation framework, and I don't want to talk too much about it, but lookup is essentially a helpful tool that allows you to fetch two related documents, merge together in one document in one step instead of having to do two steps. And this mitigates some of the disadvantages of splitting your documents across collections, because now you can at least merge them in one go. Let me show you how it works. Here we got our book offer example still. And now let's say I want to fetch all my books with the offer data included. To do that, I can use my books collection, and use the aggregate method. Again, this uses the so-called aggregation framework, and we'll have a look at this later in the course in detail. There you pass an array because you can define multiple steps on how to aggregate your data. For now, there's only one step I'm interested. A step is simply a document you pass to the array, and that is the lookup step, $lookup. That step is configured by passing a document as a value, and here you need to define 4 things. I simply brought this into a new page to make it easier to read. So 4 things need to be defined here. The first one is the from thing. And the question here is, from which other collection do you want to relate documents? So here we're running aggregate on the books collection. So we want to pull in other documents from the offers collection. So that is the name of the collection where your related documents live in. You then define the local field. So in the collection you're running this on, so the books collection, where can the references to the other collection be found in? And for books, we stored that in the offers field. Offers simply is an array of object IDs. Now we need to tell MongoDB, okay, I know where your keys are stored. Which field are you relating to in your target collection? So in the offer collection here, the offers collection. And you define that with the foreign field key. And there we know it's an _ID. Please note that all these values are enclosed in double quotation marks. Offers, and here my _ID field. So I know that in offers, in books, I have object IDs stored where the matching equivalents can be found in _ID in the offers collection. Last but not least, you give this an alias under which this will be merged. And I'll name this creators. The name is up to you here. If you hit enter, let's print this, we get back this result. What we see here is we got our book, actually all the books we have in there, only one in our case, with the name, with the offers and the object IDs, but then a new key was added, creators. And that actually holds the offer data which lived in a different collection and which was merged into our result by the aggregate and lookup function. So this is very useful for merging data in one step, and it allows you to get the best of both worlds, having it split up and still fetch it in one go. Now, this still is not an excuse for always using references, because obviously this costs more performance than having an embedded document. So if you can and if your application needs it, go for embedded documents. If you have to use references, or if you want to use references, well then this lookup step in the aggregate method can at least help you get the data you need. Now, it was just a first look at aggregate. As I mentioned, we'll have a whole module where we see what else aggregate can do for us. Be aware of lookup for merging your relations though. Okay, so we learned a lot about schemas and relations. Let's practice that a bit. And here's a simple example project which I want you to think about how you would structure the data for it. And then of course we'll also do it together. So we have our user in our application, and that can be a server-side rendered website, a single page application, a mobile app, anything like that. We got our app server. And in that app server, or to that app server, we send a couple of different requests. Because let's say we're building a blog, as the title says. So users are able to create posts, edit posts, delete posts, fetch all posts so that we can display a list of posts on a page, fetch a single post so we can read that post, and also comment posts so we can write comments. And we can also fetch these comments, of course, to display them. Now, we got our application server with our code being written in Node.js and .NET, PHP. We won't write the code here. This is not a web development course. We won't write any code here. We'll just structure the data for that and see how such a dummy request, how such a write or such an edit could look like. Our code in a real app would of course use the Mongo driver. We will use the shell here, and in the end, it'll send the data, the requests to the server. So our goal here now in this exercise is to simply define a schema, identify the core entities we have in this world, and how the schemas for these entities could look like, how they are related, and how we would model these relations. And then we'll just play around with some queries so that we can see how our application, how the MongoDB driver would interact with our database. So let's have a look. I'm drawing on my iPad here, and as I mentioned, definitely go ahead, do this on your own. Definitely lay out the core data entities you have and how they might look like in your application and how they could be related. There is no single correct solution here, but I'll go, well, with my approach now. So which kinds of data do we have? Well, in our single block, we have at least a user. We have our posts, so we have a single post. And we'll also have a comment, because users can comment posts. So these three data entities here should exist. Now, which kind of data does a user consist of, does a post consist of, and does a comment consist of? They will all have that underscore ID, of course, because that is a hard requirement by MongoDB. Then a user might have a name, might have an age, and might have an email, let's say. A post might have a title, might have a text, and whatever else you want, maybe some tags. And obviously, you might come up with totally different fields here. Now, that is how that could look like. A comment will simply have some text, let's say. How are these entities now related? Well, a user can create a post and, of course, edit and delete it then. A user can also comment a post. So a post can have multiple comments where each comment also knows which user created the comment. These are the general relations we have in there. How could we now model that? Well, we got the whole variety of things. We could embed everything. We could go with one collection only. Let's say the post collection is our only collection we want to go with. And in posts, we then have our user, and that is an embedded document which holds the user data as defined here. And in post, we also have our comments, which is basically an array of nested documents. Sorry for my super ugly drawings, but here we would have that comment data in an array. So this would be the only collection we then have. Posts with embedded users in a single post, or the embedded user, and embedded comments. Now, is that a good approach? Well, parts of it are good. I'm fine with embedding my comments here, because the comments are a one-to-many relationship. A post can have many comments, but a comment always belongs to one post. A post also typically doesn't have millions of comments, so we probably don't hit any MongoDB limit, and we often want to fetch a post along with its comments. So nesting the comments here might be fine. You can always go for a different solution, but I'm fine with nesting comments. What about nesting the user? I don't think that is a good idea. Nesting the user doesn't sound too good to me, because if we nest a user here, then we have a problem, because one user can create many posts. So if the user data then changes, let's say if the email changes, we have to edit that user in all the posts. So we got a lot of duplicate data. And whilst that might not change on a daily basis, it certainly is not like a user never changes any data. So it's not such a low frequency that I would be fine with doing all these duplicate changes when they occur. So I'm a fan of actually creating two collections here. The users collection and the posts collection. Will not have a comment collection. We'll have comment data in this structure in our array here, but we'll not have a separate collection for comments. Instead, we'll have posts and users, and we'll use these collections with some embedded documents for comments and also for tags, by the way. Tags also in the end is just an array of strings, so we could also say that this is a relation to different tags. So we have two major collections, posts and users. This is my solution, and I hope my explanations here are clear why I would not use a comments collection, even though you can of course do that, and why I would not use nested users. Now, let's go back to the shell and play around a bit with that and see how we could implement that there. So let's go from drawing to database action. I'll go to my block database, and there I said I want to use two collections. Let's start with the users collection. There, let's say I insert many users. We got multiple offers on our block. Now, insert many takes an array of documents where each document is one element we insert into this collection. A user here can have a name, Max Schwarzmuller, can have an age, 29, and let's say an email address, max@test.com, which is not my real address. I also have a second offer, Manuel Lawrence, age 30, and also email here, manu@test.com. If I hit enter, these two elements get inserted, and obviously we can now print them. This is the data in our users collection. Now let's go to our posts collection. So posts, there I want to insert one post, let's say. Obviously we could insert multiple posts. Now, one post can have a title, my first post. A post can also have some text which holds the actual content. This is my first post, I hope you'll like it. And this could be very long text. As you learned, the text type is able to store very long text. We might also have some tags here, and that could be an array of strings, like new, tag, whatever your tags are. And now we come to the relations. Now, my relation here is that this post is written by a user. Let's name it creator. And this could be a list if you have multiple offers in your application. Let's say in this application, and that is totally up to you, of course, we only have one offer per post. So my creator or offer, however you want to name it, here should be one of my users. And let's say this was written by Manuel. So I'll copy that object ID. We could match it by any key, of course, but we should ensure it's unique, and the object ID is ensured to be unique. And I'll therefore set this as a value for creator. Now we also might have comments here. And let's say we got a couple of comments there, and each comment then is another document. So here I got a list of documents where I have some text. I like this post. And as another key here, I don't just have the text, but also the offer of this comment. And that again would be the ID of a user. So let's grab Max here maybe. Grab that object ID here and insert this as the offer. So here again, I'm also using not an embedded user for the same reason why I'm not using it on a post. I'm not using it on a comment either. Instead here I also use a reference. Let's hit enter. This worked. And let's have a look at our post. This is how it looks like. And this post has the fields I sketched out. And most importantly, we have a reference relation to the person who created the post. But we got an embedded document, or even multiple documents, for the comments, where each comment in turn also has a reference relation to the offer. This is how our block could look like in code, so in the database, and I also explained why I would structure it like this. And this example, together with the previous lectures, hopefully gets you into the right mental model on how to think about this, and hopefully helps you with your next projects to structure your data and your relations in a way that makes sense for your application, to your size of data, the amounts of data, the frequency with which you change it, and your overall structure or relation that is imposed onto you. by your application. We talked a lot about schemas, structures, relations. Now let's talk about schema validation, and with that I'll come back to the data type thing and also to our schema structure in general. You learned that MongoDB is very flexible. You can have totally different schemas or documents in one and the same collection. And that flexibility is a huge plus. But sometimes you want to lock down your flexibility, you want to get rid of it. Sometimes you need a strict schema because you know your application is going to fetch posts and it is going to access the title on each post, and it does expect that each title is a string. And for cases like this, schema validation can help you. Now, what is schema validation? Let's say we have an insert operation going on our collection, on our posts collection maybe. And the same would be true for update or insert many operations, by the way. So we're trying to add or edit some data in a collection. If we add a validation schema, and I will show you how you add one in the next lecture. If we added one, then the schema will validate, or the MongoDB will validate the incoming data based on the schema we defined. And it either accepts it and then allows the write to the database, or it rejects the incoming data. Hence, your database is not touched and is not changed, and the user gets an error. To be precise, you can define schema validation in the way I'll show it in the next lecture, and you can also define which kinds of operations you want to validate and what you want to do if validation fails, with 2 settings you can add. You can define which documents should get validated and what happens if it fails. You can either set the validation level to strict, which means all inserts and updates are checked, or to moderate, which means all inserts are checked, but updates are only checked for documents which were valid before. So if you had some invalid data in there because it existed before you set up a schema, then you could still change these documents even if they don't fit your schema. For validation action, you can decide whether you want to throw an error and not go on with the insert or update, so it will not change your database data, or if you only want to log a warning and proceed. So then you would still write the data, you would still change the data, but log a warning that it did not fulfill your criteria. And what you want to choose here really depends on your application. If you're okay with incorrect data ending up in your database, you just want to be aware of it, or if you totally need to block it. Let's have a look at that in code next. So we want to add validation. And actually, I want to use my posts example here. Now, how can you add validation in MongoDB? A very easy way of adding it is when you add a collection for the first time. So when you create a collection. And you learned that the collection is created automatically when you start inserting data into it. So here, let's say I want to drop my posts collection. So now if I try to find one post, that will not work. Now let's create the collection differently. Not implicitly once we add something, but explicitly. For that, we got the create collection command. We didn't use it thus far because often that lazy creation, where it only gets created if it's needed, is okay. But if you want to configure your collection a special way, well, then you can use that create collection command. There, you first of all, as a first argument to the create collection method, define the name of the collection. In our case, it would be posts. So previously, you just accessed it and started working with it. Now you create it, and therefore you have to define the name here. The second argument is a document where you can configure that collection. And one important piece of configuration here is the validator. The validator key takes another sub-document where you can now define a schema against which incoming data with inserts or updates has to validate. You do this by adding a JSON schema key, $JSON schema key here, JSON schema, and then again another nested document. And this now holds the schema. So here we're just saying, hey, our validator is the JSON schema. Historically, there were other validators, but it is strongly recommended to go with JSON schema now. And then you define the schema here in this nested document. Now there, you can define a schema for every document which is added to the collection. For example, we can set the BSON type here to object. So everything that gets added to the collection should be a valid document or object. More interestingly, we can set a required key here, which is an array. And here we can define names of fields in the document, which will be part of that post collection, that are absolutely required. And if we try to add data that does not have these fields, we'll get an error or warning, depending on our settings. So here, we simply pass the names of the fields. Like in our case, for the post here, we could say a title is required and a text is required. Maybe tags are not required. The creator is required though, so creator, and the comments, let's say, are also required. So now these 4 fields are required on every document that gets added to the posts collection. Now we can even dive a bit deeper and start working on our properties. Now, since this gets a bit hard to read, let me actually take that entire command here and move into a text editor where this is easier to read. I created a validation.js file. It should be a JS file if you're using a tool like Visual Studio Code to get nice syntax completion. The name does not matter at all. And I'll paste in my command and use the auto formatting capabilities of that IDE, which you can find by inspecting the key bindings there under Preferences, Keyboard Shortcuts, and then Format Document is what you want to look for. This shortcut here, I use that to format this in a nicer way. So this is what we wrote thus far, a validator with a schema for the overall document. And now we can add a properties key, which is another nested document where we can define for every property of every document that gets added to the posts collection, how it should look like. For example, the title field. Keep in mind, title is required here. By the way, that is incorrect. Every element here should be a separate string, not one big string. So like this, it should look like this, 4 strings. So title is required, and now we can define it in even more detail. We can not just say it's required, which is already done here. We can say the BSON type here should be string. And that comes back to the data types you learned before, and also consult that lecture I added earlier where you see a list of all the data types, because you'll need to type as it's noted in the MongoDB documentation here. So only strings are accepted as titles. You can also add a description here, so must be a string and is required could be added here. And we can do that for all our properties now. So for the text too, what would that be? Well, it would also be a string. And we can also pass a description here, which is just the same description as up there. The creator, on the other hand, that would be a BSON type of object ID. Here the MongoDB equivalent is object ID written like this as a string. So here we can also add this must be an object ID and is required. We also have our comments here, and the comment has a BSON type of array, because in our post we got multiple comments. So we can also add a description, must be an array. And of course, our comment, since we have multiple items in there, you can add an items key here, which describes how the items should look like in that array. There you can set the BSON type to object, because every item will have to be a document. It's not allowed to be a string, it will have to be a document. Well, and in our comments, as we added them before, we had a text and an author. So we'll again add a properties key here, and now basically say, well, every item in the array has a text field, which in turn is of type or BSON type text, where we can have a description must be a string and is required. And for it to be required on the items in the array, we should add the required key and say that text is required and that author is required. And then down there in the properties setup, we can also add, or we should add the author and say, well, the author, Here the beast type is object ID. And we also have a description must be an object ID. And is required. Now you can find this document attached to this video in case this was too fast. In the end, I'm defining a simple schema on how you can validate incoming data for our posts collection. And I'm doing this when we create the collection. So we can copy that entire command now and move back to the shell. And of course, at the end of this module, you'll find a link to the detailed official docs with all validation options. So I can enter this command here, and I got an error here. Object ID is not understood, and indeed that is correct. It should be object ID with a capital I. In the file which you download, this will already be fixed. I fix it here manually, and I also had a problem here. The beast type of text is not text but string. I did that correctly up here. Simply reuse text here. That should be string. Again, in the document you download, this will be fixed. With that added, let's now add it here. We get OK. And now, if I look at the posts, there's nothing in there, of course, still. But now let's insert a document. And for that, I'll repeat my previous insertion with title, my first post, text, and so on. If I hit enter, this succeeds. So now if I find one post, this is the post I added. Now let me try inserting something where my author is not an object ID, let's say, but a random number, because maybe I have authors stored which I want to match by that number which fits another field. Now I get an error. I get an error in the end which says document failed validation. And that is a pretty clear error, right? We failed validation. And if I now look into my posts with find to see all posts in there, we actually see indeed the post was not added there because we just get an error telling us that we failed. So validation works and it didn't add our incorrect post. Now let's play around with the additional settings we can set, which I already showed on my slides. For these settings to activate, I would need to create my collection again and set up the validation again. The problem is, I of course already have my validation turned on here. So what can I do? As a database administrator, and this is how you would add such settings like validation, you can use db-run command in the shell here. To run, well, an administrative command, you pass a document with information about the command. And here, the command is that we set a call mod, that stands for collection modifier, and we define the collection which we do want to modify, posts in my case. And then we can again pass a validator. So now we can pass exactly what we passed to create collection. So we pass validator and then the entire schema below that. So make sure to grab that portion of the file, go back to the shell. Now important, remove the closing parentheses, add a comma, and paste in what you just copied. And then add another closing curly brace and closing parentheses. But we're not done here. If I hit enter like this, of course, it works, but now I just set the same validation again. What I instead want to do is, I want to change my validation settings. So I'll add a new file, which you also find attached to this video then in the finished form, where I copy my create collection code into. Now here we will have run command as you just saw, then we pass our opening curly brace, call mod, then holds the name of the collection we want to edit, and then I need to remove that curly brace here, can reformat. This is now the command, and now here I got my validator, but now I also want to switch an additional setting. Now let's search for the closing parentheses of validator, because we need to set our validator configuration as a sibling to that validator key here. So for my IDE, it conveniently highlights this. After this, we can add validation level to control whether all inserts and updates are checked or only updates to elements which were valid before. But I want to set a validation action here. The default is error, which blocks the action and throws an error. I'll set it to warn. Let's copy that entire code. Again, you find it attached to this lecture. And execute it here. Should be successful. And now if I again try to insert one post with my offer being, or having a value of 12, which is not an object ID, this actually succeeds. And the only thing it did is it will have written a warning into our log file. And the log file is stored on our system. We'll have a look at this in a later lecture when we talk about configuring our server and so on. So this is the difference. Now what you want to use here depends on your application and your requirements there. It's good to know that you can configure these things, and putting validation in place can make a lot of sense depending on how your application works, how important it is for you to have one consistent scheme of data. And you also now saw that you can define that validation schema when you create the collection or also thereafter with the help of run command. That's it for this module. And I want to conclude it with a wrap-up. And the first important thing in this wrap-up is that I reiterate how you should think about data modeling and structuring. Consider the format in which you'll fetch your data. How does your application or your data scientists, how do they need the data? You want to store your data in a way that it's easy to fetch, especially if you're building an app or if you're having a use case where you fetch a lot. Because that's the next important question. How often do you fetch data and how often do you change it? Do you need to optimize for writes or for reads? Often it's for reads, but it could be different for you. If you write your data a lot, you should definitely avoid duplicates. Make sure you got no duplicates. If you read a lot, maybe some duplicates are okay if these duplicates don't change that often. Basically what I covered when walking through the different relation setup options. Also keep in mind, how much data will you save and how big is it? Do you store all citizens of New York City? Maybe embedding the data is not your best choice then. How is your data related in general? One-to-one, one-to-many, many-to-many? This often gives an indication for whether you want to go with embedded documents or references. And in general, will duplicates hurt you? Do you update your data a lot, in which you have to update a lot of duplicates? Do you maybe have snapshot data like with orders and products, where you don't care about updates to the most recent data, to your products data? And finally, will you hit any data storage limits? Like, do you need to embed 100 levels deep, which is the limit MongoDB imposes? It's not very likely, but that is something you should at least be aware of and which you should keep in mind. With that, here's the general summary. In this module, we had a detailed look at how you model schemas. That this can make sense even though MongoDB does not enforce a schema onto you, because your application typically needs data in a specific structure. Important factors are the factors I just mentioned: frequency, relations, size, and so on. You also learned about data types there, by the way. Text, integers, long integers, decimals, and I will also come back to the numbers later in this course. We also had a detailed look at relations in this module. You basically have two options: embedding or references. And you want to use embedded documents if you got a one-to-one or one-to-many relationship, and if it makes sense for your app and the way you interact with your data, with all the points I highlighted throughout this module and a few seconds ago. References make sense for many-to-many relationships, or if you want to fetch data separated, or if you got very large amounts of nested data, like New York City with all its citizens. Exceptions are always possible, and there is no hard rule like many-to-many should always use references, as you saw with the example of products and orders. But keeping an eye on your app requirements and how your app works and interacts with your data gives you a good clue and indication of how you want to structure your data typically. Last but not least in this module, we had a look at schema validation, which allows you to enforce a certain set of rules on incoming data so that no invalid data ends up in your database. You learned how you can define such rules and how that works with JSON schema, and you also learned that you can configure how your rules are applied if actions get blocked or if they just get a warning logged to the log files. This is it for this module. And with that, you hopefully got a good understanding of how you have to think about structuring data and how you can then implement your structure, relate your documents, and validate incoming data.